Welcome to the AI Research Roundup. I'm Alex. Alright, welcome back to the AI Research Roundup. Today, we're looking at a paper from the Hugging Face trending list, published on July 31st, 2025. So, just yesterday. This paper introduces a new framework for robot learning that achieves a really impressive 90.1% success rate on the Libero benchmark. The paper is titled Villa X, Enhancing Latent Action Modeling in Vision Language Action Models, and the way it achieves these results is by rethinking a key concept. The core idea is to improve how robots understand latent actions, which are abstract representations of visual change, by grounding them in the robot's own physical movements. Also, the authors shared their official repository, and it's a great resource for anyone wanting to dive in. You'll find the pre-trained latent action model, inference code, and even a Jupyter notebook that provides a step-by-step guide. It's a fantastic starting point for experimenting with their work. On the Villa X Hugging Face page, you won't find downloadable model weights, but it links directly to the project's GitHub for code and usage instructions. So let's look at how this Villa X framework actually works. The first figure gives a great overview. We see two main parts: a latent action model, or LAM, which infers abstract actions from images. Then, an actor module uses that latent action, an image, and text to create a plan for the robot. The diagram on the right details the key innovation within the latent action model. It adds a proprio forward dynamics model, which grounds the latent action by forcing it to predict the robot's future physical state and movements. Building on that idea of a grounded latent action model, this next figure gives us a great visual. It shows different pairs of images that the model has identified as having a similar latent action. So, in the column labeled Pick Things Up, we see different robots, in completely different settings, picking up various objects. The model has learned to see all of these as the same fundamental action. This really highlights the model's ability to generalize across different robots and environments, capturing the core concept of an action rather than just its specific visual appearance. So how does the model use these generalized actions to actually plan? This figure breaks down the actor module, which is the part that decides what to do. It starts with a vision language model, processing a text command and an image. Then, a component called ACT Latent generates a sequence of future latent actions, creating a high-level plan. Next, the ACT robot component takes that plan and turns it into low-level robot movements. The key here is the unidirectional attention, meaning the robot action planner explicitly follows the latent action plan, creating a clear bridge from goals to control. This table then provides the hard numbers to back that up. The authors test different versions of their model on the simpler benchmark, which is a simulated environment designed to test robot manipulation with two different robots. The top row, ours, is the complete Villa X model. It achieves an impressive average success rate of 55.4% across these tasks. Now compare that to the second row, a version without the proprio forward dynamics model. Its performance drops to just 42.6%. This clearly shows that grounding latent actions in the robot's physical dynamics is critical for success. Alright, so now we see a broader comparison. This table pits Villa X against several existing methods on the simpler benchmark, using two different robots. The models are grouped into standard vision language action models and other latent action-based methods, and across the board, Villa X comes out on top. It scores the highest average success rate on both the Google robot at 59.6% and the Widow X robot at 62.5%. This really highlights that its specific way of using latent actions is more effective than previous approaches. Moving from simulation to the real world, this next table shows how Villa X performs on an X-arm robot equipped with a highly complex 12-degree of freedom dexterous hand. The tasks here are much more intricate, things like stacking cubes and pouring water. The results are split between seen scenarios with familiar objects and unseen ones that test generalization. Across the board, the full Villa X model, the bottom row, significantly outperforms the baselines. This is especially impressive because it learned to control this new hand without any prior dexterous hand training, showing incredible embodiment transfer. So, in conclusion, the success with that complex hand really drives home the core ideas of Villa X. By grounding abstract actions in physical dynamics and using them for explicit, high-level planning, the model achieves impressive generalization across different robots and challenging tasks, both real and simulated. That's it for this episode of the